Deep in the universe, billions of light-years away lies a cosmic giant known as the Phoenix Cluster. This cluster of galaxies is a behemoth, a gathering of thousands of galaxies bound together by gravity. What makes the Phoenix Cluster truly extraordinary is its heart, a region ablaze with the light of newborn stars. Galaxy clusters, despite their enormous size and grandeur, are not typically known for their stellar nurseries. They are often depicted as serene cosmic landscapes where star formation has long since ceased. The discovery of a vigorous starburst in the Phoenix Cluster, therefore, came as a surprise. This unexpected discovery, a testament to the universe's capacity for wonder, has forced us to reconsider our understanding of these cosmic giants. It suggests that galaxy clusters, far from being dormant, can be sites of intense star formation, challenging our preconceived notions and opening new avenues for exploration. Unveiling the secrets of the Phoenix Cluster required a new generation of telescopes, instruments with the power to peer deep into the universe and capture the faint light from distant galaxies. Leading this charge is NASA's James Webb Space Telescope, or JWST. The JWST, with its large infrared telescope and advanced suite of instruments, can detect the heat signatures of star formation even in the dustiest corners of the universe. This makes it the perfect tool for studying objects like the Phoenix Cluster, where dense gas and dust obscure visible light observations. In its observations of the Phoenix Cluster, JWST captured detailed images and spectra, revealing the presence of vast amounts of warm gas. This warm gas, a key ingredient for star formation, provided the first clues to the extraordinary starburst occurring within the cluster. Stars, the building blocks of galaxies, form from the collapse of giant clouds of gas and dust. These clouds, known as nebulae, are often vast and diffuse, stretching across light-years of space. Within these nebulae, regions of higher density can begin to collapse under their own gravity, initiating the process of star formation. As the gas and dust collapse, they heat up and form a protostar, which will eventually ignite nuclear fusion in its core and become a new star. This process, a delicate interplay of gravity, pressure, and temperature, is most efficient in environments rich in cold, dense gas. These conditions allow the gas to collapse more easily, leading to the formation of new stars. However, not all regions of space are conducive to star formation. The presence of other forces, such as magnetic fields and turbulence, can hinder the collapse of gas clouds, making star formation a complex and often inefficient process. Galaxy clusters, however, are typically filled with a different kind of gas, a hot diffuse plasma that permeates the space between galaxies. This plasma, often heated to extreme temperatures by the gravitational forces within the cluster, is not conducive to star formation. The high energy of the particles in the plasma prevents them from cooling and collapsing into new stars. This hot gas, heated to millions of degrees by the cluster's gravitational pull, is too energetic to collapse and form stars. The energy within the gas keeps it in a state of high pressure, preventing the gravitational forces from pulling it together into denser regions where star formation could occur. This is why most galaxy clusters are not sites of active star formation. The JWST observations of the Phoenix Cluster, however, revealed something unexpected: the presence of a significant amount of warm gas. This warm gas, with temperatures lower than the surrounding hot plasma but higher than the typical cold gas found in star-forming regions, presents a unique environment. The discovery of this warm gas challenges our understanding of the conditions necessary for star formation in galaxy clusters. This warm gas, cooler than the surrounding hot plasma but warmer than typical star-forming gas, appears to be fueling the cluster's starburst. The presence of this intermediate temperature gas suggests that it may be able to cool and condense into new stars, despite the generally hostile environment of the galaxy cluster. This starburst activity indicates that the Phoenix Cluster is undergoing a period of intense star formation, driven by the unique properties of the warm gas. This discovery suggests that the Phoenix Cluster, unlike most other galaxy clusters, may have found a way to cool its hot gas and trigger a new wave of star formation. The mechanisms behind this cooling process are still not fully understood, but it opens up exciting possibilities for the study of galaxy clusters and the conditions that can lead to star formation in these extreme environments. The Phoenix Cluster serves as a fascinating case study in the complex interplay of gas dynamics, temperature, and star formation in the universe. Section 4. An outlier in the cosmos. The uniqueness of the Phoenix Cluster. The Phoenix Cluster, with its vigorous starburst and abundance of warm gas, stands out as an anomaly among its peers. Unlike most galaxy clusters, which are relatively dormant, the Phoenix Cluster is teeming with activity. This cluster is a hotbed of star formation, with new stars being born at an astonishing rate. The presence of warm gas fuels this stellar nursery, creating an environment that is both dynamic and fascinating. Most galaxy clusters, as mentioned earlier, are relatively quiescent environments, where star formation has long since subsided. These clusters are often dominated by older galaxies, where the birth of new stars is a rare event. The contrast between these typical clusters and the Phoenix Cluster is striking. Take, for example, the Coma Cluster, one of the closest and most studied galaxy clusters. The Coma Cluster is a prime example of a typical galaxy cluster where star formation is minimal. The Coma Cluster, unlike the Phoenix Cluster, is dominated by old red galaxies, a telltale sign of a population of stars that formed long ago. These galaxies have long since ceased forming new stars, and the cluster as a whole is a relatively calm and stable environment. Star formation in the Coma Cluster is minimal, a stark contrast to the bustling stellar nurseries of the Phoenix Cluster. The difference in star formation activity between these two clusters highlights the unique nature of the Phoenix Cluster. Another example is the Perseus Cluster, a massive galaxy cluster known for its powerful radio emissions. The Perseus Cluster is an active and energetic environment, but even it does not match the star formation rate of the Phoenix Cluster. While the Perseus Cluster does exhibit some signs of ongoing star formation, it pales in comparison to the starburst observed in the Phoenix Cluster. The Perseus Cluster's star formation is modest, whereas the Phoenix Cluster is a veritable explosion of new stars. The Phoenix Cluster, therefore, appears to be an outlier, a unique laboratory for studying the processes that can drive star formation in the most extreme environments. Its exceptional characteristics make it a valuable subject for astronomers seeking to understand the complexities of galaxy formation and evolution. The Phoenix Cluster's vibrant activity offers a glimpse into the dynamic processes that can occur in the universe, providing insights that challenge our understanding of how galaxies and stars are born and evolve over time. Section 5. Cosmic Puzzle. Unraveling the mystery of the Phoenix Cluster. The discovery of the Phoenix Cluster's starburst has presented astronomers with a cosmic puzzle. This cluster, located about 5.7 billion light-years away from Earth, is unlike any other. Its extraordinary rate of star formation has left scientists both intrigued and baffled. The Phoenix Cluster is producing stars at a rate of about 740 solar masses per year, a phenomenon that is rarely seen in the universe. What makes this cluster so special? The Phoenix Cluster stands out because it defies the typical life cycle of galaxy clusters. Most clusters have long since ceased their star-forming activities, having exhausted their gas supplies or heated them to temperatures that prevent cooling and subsequent star formation. Why is it able to sustain such a high rate of star formation when other clusters have long since quieted down? This question has led researchers to explore various hypotheses. One leading theory involves the central galaxy of the Phoenix Cluster, which appears to play a pivotal role in this cosmic anomaly. One possibility is the role of the central galaxy. This galaxy, located at the heart of the cluster, is not just any galaxy, it is a massive, active galaxy with unique properties that could be influencing the entire cluster. At the heart of the Phoenix Cluster lies a supermassive black hole, a gravitational behemoth that is actively feeding on gas and dust. This black hole is millions, if not billions, of times the mass of our Sun, and its voracious appetite has significant consequences for its surroundings. This feeding process releases enormous amounts of energy, creating powerful jets and winds that can heat the surrounding gas. These jets and winds are not just random outbursts, they are highly energetic phenomena that can extend over vast distances, influencing the entire cluster. In the case of the Phoenix Cluster, these jets and winds may be playing a crucial role in regulating the temperature of the cluster's gas. By preventing the gas from cooling too rapidly, they create a delicate balance that allows for the formation of warm gas, which is essential for star formation. They may be preventing the hot gas from cooling too rapidly, creating a balance that allows for the formation of warm gas and the subsequent birth of stars. This balance is a delicate one, and any disruption could halt the star formation process. Another possibility is the cluster's recent merger history. Galaxy clusters are dynamic systems, and their interactions can have profound effects on their evolution. Galaxy clusters, like galaxies themselves, can collide and merge, a process that can trigger bursts of star formation. These cosmic collisions can funnel gas into the central regions of the cluster, providing the raw material needed for new stars to form. It's possible that the Phoenix cluster is the product of a recent merger, and the starburst we observe is a consequence of this cosmic collision. The merger could have reignited star formation by compressing gas and creating shock waves that trigger the birth of new stars. This combination of factors makes the Phoenix cluster a fascinating subject for ongoing research, as astronomers continue to unravel the mysteries of this extraordinary cosmic phenomenon. Section 6. A new era of discovery, future research and unanswered questions. The discovery of the Phoenix cluster's starburst has ushered in a new era of discovery, raising more questions than answers. What is the precise mechanism that allows the cluster to cool its hot gas and form stars? How common are starbursts like this in the universe? Answering these questions will require further observations and modeling. The JWST, with its unprecedented sensitivity and resolution, will continue to play a crucial role in unraveling the mysteries of the Phoenix cluster. Future missions, such as NASA's planned Nancy Grace Roman Space Telescope, will build upon these observations, providing even deeper insights into the cluster's structure and evolution. These telescopes, combined with sophisticated computer simulations, will help us paint a more complete picture of the Phoenix cluster and its place in the grand tapestry of the cosmos.